and gentlemen. Today, let's talk about lesson 7.6, which is exponential growth and decay. So what we're going to do is we're going to take all of the skills that we learned, especially those that we talked about in our last lesson, and we're going to start applying them to real-world situations. So to do that, we've got two skills to work on. The first one is that we're going to use those properties of exponents to interpret expressions for exponential functions. And then the second one we've been working on all along, we're constructing those exponential functions given different information. So our first vocab term today is the idea of exponential growth or decay. So now we're going to apply it to that real world situation where we have an amount that is increasing or decreasing by the same percent over a given time. And I'm going to write it in the form y equals a times the quantity 1 plus r raised to the power of t. And now if I think back to my generic form for exponential growth, I had that idea of y equals a to the power, or ab to the power of x, and then sometimes plus that c, the less important part at this point. But that b value, that middle piece now, the amount that I'm increasing or decreasing, I'm going to write as a decimal. And then if I have 1 plus that decimal, or 1 minus if it's a negative number, I can show that growth or decay. So my final amount is going to be equal to the initial amount, or that starting value. Same thing as when I was talking about graphing. I had that starting value times the amount that I'm growing raised to a power, and this time power is time. Well, the other piece that I'm going to do with this is I can show compound interest. So again, I'm talking about that same generic form where I have y equals ab to the power of x. But this one here, it's an application of exponential growth to show interest earned or paid on an initial investment and previously earned interest. And so this one has some real world implications for you guys. We're going to do an example in this video here about a car loan. These are things that you will encounter in your real life. Like our other one, we have that final amount, the amount that we pay or are paid, as our output, but our input is our principal, or the initial amount, multiplied by that rate of change. But in this case here, we need to express the rate of change divided by the number of times that interest is compounded each year. And the power is going to be the number of times the interest is compounded multiplied by the number of years. So we'll practice with this so you can see what it looks like. Our first practice problem is one of your 6 homework problems tonight, so I'm going to get you started on it. The median house price in the United States increased an average of 1.4% each year between 2005 and 2007. Assume the pattern continues. And now a little side note here. Things like this, the pattern wouldn't necessarily continue. If you think about the recession in 2008 or the pandemic, anything like that can affect it. But this piece here, assume the pattern continues, tells us that we're just going to use the mathematical representation of this value here. So if I want to write the equation for the median house price for t years after 2007, I need to think about the form of my equation. So exponential growth is going to be in the form y equals a times 1 plus that rate raised to the power of t. So I need to figure out what I know. Y is going to stay the same. I want to know the equation here. The a, the starting value, well in 2007, I see from this picture here, the median house price was $247,900. I want 1 plus the rate. Well, it increased an average of 1.4%. Percent tells me 1.4 per 100. That means I move my decimal 2 spaces over, and 1.4% is equal to 0.014. And I'm going to raise it to the power of t years. The only other thing I want to do to finalize my equation here is I want to simplify anything that I can. And so this inside piece here, I can simplify inside the grouping symbol. My final answer is going to be y equals 247,900 multiplied by 1.014 to the power of t. And what you should notice is by thinking about that generic form, y equals a times b to the power of x, is that the inside piece, that b value, should be greater than 1 if I have growth. If it's between 0 and 1, I should have decay. So now I want to use that equation to predict the median house price in 2018. Well, 2018 is going to be 11 years after 2007. So I want to know 11 years later, what value do I have? So I'm going to take my equation and I'm going to plug in a value of t equals 11. So I get y equals 247,900 multiplied by 1.014 to the power of 11. And I can type that in on my calculator. I know my order of operations tells me I need to do that exponent before I can do anything else. So 1.014 to the power of 11 is 1.165245689. What I want to do is I want to go on my calculator and I want to use it. I want to just take that answer or click again and multiply that value by 247900. My final answer is 288,864.4063. 1, 2, 3, column. 288,864.4063. The last thing I want to do, and this one here, well, two last pieces I need to do. This is a word problem, so I need to label my answer with the units. But the other thing that I need to do is I need to think about what would be a reasonable value to round my number to. Because I'm talking about money here, one way you could argue it is that I should round to the nearest cents. So I should round to the nearest hundredths place. But if I look at the way that my values were written for median home price initially, they were all rounded to the nearest hundredth. So I think it would be more reasonable to round my final answer to the nearest hundredth. Now, if I were giving you this problem on a test, I would tell you what to round to. But in this case here, I just want you to think about what would be a reasonable spot to round to. So my final answer, 864 rounds to 900. 288,900. If you gave me the other one or rounded it to the nearest cents or the nearest tenth or the nearest dollar, that would be acceptable. But I think in this case here, rounding to the nearest hundredth makes sense based on the information that we were given initially. Well, now for this next part, we're going to talk about both exponential decay and compound interest. So I want to think about those two different equations that I'm working with in this lesson. Aiden is hoping to buy a car for $15,000. She currently has $3,000 saved up, so she'll need to take out a loan for $12,000. The dealership offers her a loan for 5 years with an interest rate of 5.2% compounding monthly. So I looked up just on the internet what's the average interest rate right now, and it said like 5.2 or 5.3. So this is real life situation here. If you're hoping to buy a car, it's kind of an expensive car, but real world situation. I want to know what the final cost will be for the car after the loan is repaid. So the first thing I need to do is I need to figure out how much is the loan going to cost. Well, then I'm going to think about that other equation, my compounding interest equation, which looks like the amount at the end is going to be equal to the principal times 1 plus that rate divided by the number of times it compounds each year to the power of the number of times it compounds each year times the number of years. So if I look at the information that I'm given, we're going to pause here. We'll come back to this. Well, using the information that I'm given, I want to know the final cost, so that A is what I'm looking for. Her principal, the amount of the loan, is $12,000. And I need to multiply that by 1 plus her rate. So 5.2% is 0.052. Compounding monthly tells me that it'll compound 12 times each year, and I want to raise that to the power of 12 times a 5-year loan. Now I just need to keep simplifying. I can simplify inside my grouping symbol, so I get 12,000 times 1 plus 0.052 divided by 12. 0.0043 repeating, raised to the power of 12 times 5, which is 60. If I keep going here, 1 plus that inner stuff raised to the power of 60 gives me 1.2962. If I multiply by 12,000, I get a value of 15,554.42. I'm going to round to the nearest cent here because I'm talking about money. So by the time that she's paid off her loan, she will have paid $15,000 on a $12,000 loan. But I want to know the final cost for the car because that includes the $3,000 that she had saved up and paid as a down payment. So she's really paid $18,000 for the car by the time she has paid it off? 18,550, oops, my face is in the way. 18,554.42. Now I want to think about, if she's paid that much, how much will the car be worth? Well, let's finish this out now. So that car that she just paid for, over the life of the loan, she will have paid over $18,000. But used cars depreciate at a rate of about 15% annually. How much will her car be worth when she's finished paying off the loan? So this 15% is a little squishy here, but in general, that's a reasonable estimation for depreciation. Depreciation is just decay or negative growth here. So I'm going to be using that equation, the y equals a times 1 plus r to the power of t. So it'll be worth the original value, $15,000, multiplied by 1 minus 15%, 1 minus 0.15, to the power of 5 years. So this here I can simplify inside my parentheses, and I get $15,000 times 0.85 to the power of 5. It's going to take 5 years to pay it off. Come on, there we go. So if I take 0.85 on my calculator and raise it to the power of 5, I get 0.443705313, and I'm going to multiply that by 15,000. And I get 6655.5799695. But because this is money, I know I want to round to the nearest hundredths value. So her car, by the time she's done paying it off, her car is going to be worth $6,655.58. So she will have paid over $18,000, but by the end of it, her car is only worth $6,000. Now, does that mean she shouldn't buy the car? Well, no. That just, I want you to understand how this math works, why this has real-world implications. One thing that we could know, if she had saved up the full amount and paid for it without the interest, she would have saved herself $3,000 worth of interest, and she would have that value right away. She wouldn't have to wait till the end of 5 years when she owns the car fully. Lots of different things that you can analyze with this type of problem here. But the important part is that you understand how to calculate compound interest and how to calculate exponential growth and decay. So your job tonight for homework is page 434, numbers 1 through 4, 13, which if you watched this video, we already did together, 14, and 18. 18 is tricky. It's kind of a trick question. Think about it before you look at the key. When you're finished, check out the key on Teams, grade your work, and submit your score on PowerSchool. And know that tomorrow is our last day of this lesson, so you can expect that when you are in the building next, whether that's B-Day Friday or A-Day Kids on Monday, you can expect that there will be a notebook check. Thanks for working hard, ladies and gentlemen.